Hey everyone, welcome back to Botronix Labs. In this module, we're stepping up our game by building a full joystick controller for the Pico Pedro robot arm using 2 analog joysticks and 2 push buttons, one for control activation and one for the gripper toggle. Our goal is to control 3 joints, the base, shoulder, and elbow, with just 3 ADC channels, and to use a button to initialize the robot and enable live control. Let's jump into it. By taking a quick look at how the controller is physically assembled. On screen, you can see a photo of the internal wiring inside our custom joystick controller box. The 3D printed enclosure used here was designed by Tokyo_bird, a user on Thingiverse. Huge thanks for making such a great open source design available. If you'd like to build your own, I've included the link to the STL files in the video description below. Inside the controller, we've mounted 2 joysticks and 2 buttons. Each joystick has 2 analog axes and a push button. Included an LED for visual feedback. Everything is connected to the Raspberry Pi Pico using jumper wires, a compact and neat solution for manual robotic control. This setup will be our go-to controller throughout the rest of this course. Now let's look at the circuit diagram of this controller to understand how each component connects to the Pico. The first joystick's X and Y axes are connected to GP26 and GP27 for controlling the base and shoulder servos. The second joystick's X axis is wired to GP28, and we use it to control the elbow servo. Button 1 is connected to GP15 and is used to activate or deactivate servo movement. Button 2, wired to GP14, toggles the gripper open and closed. There's also an LED connected to GP13 as a status indicator. This wiring layout allows us to control multiple servos in real time using just a small handheld controller. In this part, we'll set up the code that lets your Raspberry Pi Pico talk to the joysticks, buttons, servos, and LED. First, we need to import the necessary libraries. These let us use the Pico's pins for reading analog and digital signals, and for controlling the servos. ADC lets us read analog values from the joysticks. Pin is for digital input and output, like buttons and the LED. PWM is for sending signals to the servos. And sleep lets us pause the program for short moments. Now let's set up the joysticks. We'll use 3 analog pins to read the X and Y axes from joystick 1, and the X axis from joystick 2. X1 reads the base rotation from joystick 1's X-axis, connected to pin GP26. Y1 reads the shoulder movement from joystick 1's Y-axis, on GP27. X2 reads the elbow movement from joystick 2's X-axis, on GP28. Next, let's set up the buttons. These are digital inputs. Button 1 is connected to GP15. We'll use it to turn control on or off, and to reset the servos. Button 2 is on GP14, and it will open or close the gripper. Now, let's set up the LED indicator. The LED is connected to GP13. We'll turn it on or off to show when control is enabled. Finally, let's set up the servos. Each servo is connected to a different pin. The base servo is on GP2. The shoulder servo is on GP3. The elbow servo is on GP4. The gripper servo is on GP5. We set each servo to a frequency of 50 Hz. Now your Raspberry Pi Pico is ready to read inputs from the joysticks and buttons, and to control the servos and LED. Now that our hardware is set up, let's make our code smarter and our robot's movement smoother by writing some helper functions. First, we need a function to convert an angle like 0 to 180 degrees into a PWM signal that the servo understands. The angle_duty function takes an angle and calculates the correct PWM duty cycle for the servo. Most hobby servos expect a signal between 500 and 2500 microseconds. This formula maps 0 to 180 degrees into that range. The result is scaled for the Raspberry Pi Pico's 16-bit PWM output. Next, let's make a function to move a servo to a specific angle. Move_servo takes a servo object and an angle, and sends the correct PWM signal to move the servo to that position. This keeps our main code clean and easy to read. Now, let's add a function to sweep a servo smoothly from its current angle to a new target angle. Sweep _ angle moves the servo 1 degree at a time, with a short pause between each step. This creates a smooth, natural movement instead of a sudden jump. It returns the new angle, so you can keep track of the servo's position in your code. Finally, let's add a function to reset all servos to their starting positions. Reset _ servos uses our sweep function to move every joint back to its neutral position. This is useful for starting up, or for resetting the robot when you want to begin a new task. With these helper functions, you can easily move any servo to any angle, make the motion smooth, and reset your robot arm whenever you need. We'll make our robot arm more reliable and easier to control by setting up a dead zone for the joysticks, tracking the state of each joint, and making sure everything starts in a known position. Let's start by defining the dead zone for our analog joystick inputs. The center value is what the joystick reads when it's at rest. The dead _ zone is a small range around the center. If the joystick moves only a little, we ignore it. This prevents the servos from jittering when your hand isn't moving the stick. Now, let's set up variables to keep track of the current angles of each servo, the gripper's state, and the button states. We use base _ shoulder _ and elbow _ to remember where each joint is. Gripper _open keeps track of whether the gripper is open or closed. Button 1 _ flag and button 2 _ flag help us know if the control or gripper buttons are pressed or released, so we only act when the button changes. Finally, let's make sure all servos start in their neutral positions when the program begins. This line calls our helper function to move every joint to its starting position, so your robot arm is always ready to go when you power it up. With these settings, your robot arm will be stable, responsive, and always start from a known position. This makes it much easier to control and prevents unexpected movements. Now it's time to bring everything together. In step 6, we'll write the main loop that constantly checks the joysticks and buttons and moves the robot arm in real time. Let's look at the main control loop. The loop runs forever, constantly checking the state of the buttons and joysticks. When you press button 1, it toggles control mode on or off, lights up the LED, and resets all servos to their starting positions. This is great for safety and for starting fresh. If control mode is enabled, the Pico reads the analog values from the joysticks. If you move a joystick far enough from the center, outside the dead zone, the code calculates a new target angle and smoothly moves the corresponding servo to that position. The base, shoulder, and elbow are each controlled by a different joystick axis. Button 2 toggles the gripper open or closed. It only triggers once per press, thanks to the button 2 _ flag variable, which prevents repeated toggling if you hold the button down. Finally, a short sleep at the end of the loop keeps everything running smoothly and avoids overloading the Pico. With this main loop, your robot arm responds instantly to your joystick movements and button presses, giving you full manual control over every joint and the gripper. Congratulations! You've built a real-time, multi-axis robotic arm controller with safety features and smooth motion. Try experimenting with different movements, or see how precise you can get with the controls. In the next module, we'll explore even more advanced features, like recording and replaying your motions. And that's it for this module. You've just learned how to build a fully manual, real-time controller for a 4 DOF robotic arm using dual joysticks, buttons, and a Raspberry Pi Pico. With these skills, you can experiment with new movements, add more features, or even start recording and replaying your own robotic routines. If you found this video helpful, don't forget to give it a thumbs up and subscribe to the Botronix Labs YouTube channel for more hands-on robotics tutorials, project ideas, and coding tips. Thanks for watching, and I'll see you in the next module.